Assalamu alaikum ji. This is lecture number 19 of our course Numerical Methods, and we were doing the topic of curve fitting. Okay, just a recap of what is the curve fitting and what are the topics we just covered. We have covered the Lagrange interpolation polynomial and Newton divided difference formula, and in the last lecture we started with the cubic splines. Okay, so what are the cubic splines? What are their benefits? Why we're using it? We just have that introduction in the last lecture with some of the conditions that we put on the cubic spline to derive the best fit curve or the curve fit using the cubic splines. Okay, so just a recap of Lagrange interpolation and Newton divided difference formula. They both give the same answer for the same degree of the polynomial for a particular data, but they, in terms of the calculation, they are different. The Newton divided difference formula are more systematic than the Lagrange interpolation polynomial, and in terms of their issues, the main issue is that when you go for the higher degree of the polynomials, it comes with the cost of too much fluctuation. Okay, so because the higher degree polynomials have the higher values of the variables, so we may encounter in most of the cases the fluctuation. Okay, so to counter this, we try to have the splines, and we discussed in the last lecture what are the issues with the linear and the quadratic splines. Okay, now coming to the cubic splines, we are able to counter that problem, which is the number of equations and the number of variables should be same. Okay, and then we start with solving the cubic spline within the data. Okay, in this particular lecture, we'll be able to have the equations by which we can find the cubic spline, and we'll see one or two examples. Okay, to solve it. So it's more of a practically how to solve that cubic splines. Okay, now just an overview of the cubic spline. S of x is the cubic spline, and it is a collection of the cubic polynomials. And in this particular problem, we just taken a data set. Our data set will be x naught, f of x naught, x1, f of x1, till xn, f of xn. So the total points are n plus 1. Okay, and between the 2 points, we will plug the cubic spline. Okay, and so there are total n plus 1 points. Then the number of cubic splines we're going to plug in are n. Okay, so x naught, between x naught and x1 we have s naught, and generally between xj and xj plus 1 we'll have sj of x, and each sj will look like this. Okay, so for example, j value naught, we will have s naught. Okay, similarly we have imposed certain condition on the cubic spline. You can see the figure of the cubic spline where you see s naught, s1. Okay, what we have seen in the last lecture is that this s naught is at x1 should give the same value as s1 at x1. So this condition is for the to connect the points, to connect the polynomials. Okay, then we impose that this condition should hold for every interior point. What are the interior points? x1 till xn minus 1. Okay, x0 and xn are the endpoints. Okay, so this condition should hold for sj of x j plus 1 equals to sj plus 1 xj plus 1. If I just try to write this in a general setting, okay, this will be like this. And then we say, okay, the derivative should also be same at this point. And the second derivative for the more smoother curve, okay, the second derivative should also be same. Okay, these are the conditions that we have plugged there, so we can just generalize them over here by just plugging the derivative at sj and sj plus 1. Okay, and similarly the second derivatives. Okay. Now coming to one more actually condition, which is that okay, S naught is valid from x naught till x1. What is the value of S naught at x naught? It is f of x naught. Okay, because S naught, we in this particular curve fitting portion, we have decided that our interpolation polynomial should satisfy the given points. Okay, so S naught is applicable from x naught to x1. So if I plug x equals to x naught in S naught, it must give f of x naught. And similarly, S1 at x1 should give f of x1. Okay. Now, if I just write over here, what is the value of S naught from just plug j is equal to 0 in this equation? Okay, you'll see S naught will be a naught plus b naught x minus x naught plus c naught x minus x naught squared and plus d naught x minus x naught cube. This, when evaluated at x equals to x naught, will give me an answer f of x naught. So if I replace x with x naught in this equation, you'll see a naught will come as f x naught. Similarly, from here I'll get a1 is same as f of x1. Okay. Now if you see in this slide, we can generally say aj is same as f of xj. Okay, this was the first thing that we have derived in the last lecture. Okay, while we're doing the using these conditions. Okay, so because what is our aim? Our aim is when we start a problem. Okay, we have a data. We have to fit a cubic spline. The cubic spline is over here. So we have to find AJs. Okay. Basic actually variables to find are AJs, BJs, CJs and TJs. We need to find them. Okay, but since once we find them, we'll be able to construct our cubic spline. Okay. Okay. Sorry. Okay. Now, if we try to use this condition, let me just we will be using this condition later on, so let me just rub it over here and then we'll use it. Okay, now if you use this condition, which is that Sj at xj plus 1 and Sj plus 1 at xj plus 1, it's a connecting point. Okay, this condition connects the two cubic polynomials. Okay, so if you use this condition, you will come at the second equation that you see in the step number 2. Okay, this is the equation that you will arrive at. Okay, and over here, what is Hj? Hj is actually, let's start with H naught. H naught is x1 minus x naught. It's a difference between the x values, consecutive, okay? Consecutive values. So what is h1? h1 is x2 minus x1. What is h2? It is x3 minus x2. What is xj? xj is xj plus 1 minus x2. Okay, so it's just the difference between the values. So in equation, in step number 2, the equation you see here, hj's are actually these things. Okay, and if you see on the right hand side, what is it? Aj's. We know the values of aj's. Okay, we already know them. They are the function values given in the data set. Okay, so we know them. By these, this equation number 2, we will be able to get the values of the CJs. So once we got the values of the CJs, you remember this condition now that the derivative should also be same at the interior points. of the connecting polynomials. Okay, and the second derivative should also be same. Sorry. Okay, so we will be able to get the two equations from there, okay, which is given in the step number 3 and 4. Okay, so by which you will be able to find bj's, because you see the expression of the bj's, it involves aj's and cj's. Okay, and we already found them, and then at the last you will be able to find dj's from the values of the cj's. Okay, so if you go this particular way, that you start with finding aj's first, then cj's, then you have an option of the bj's and the dj's. So then you'll be able to find all the unknowns that we're trying to find. Okay, now coming to one of the conditions that we actually ends our last lecture at that point. Okay, I just have to recall that. Hopefully you remember from the last lecture, in the cubic splines, total unknowns are 4n. Okay, we got total 4n unknowns. So these are the unknowns we have. 4n minus 2 unknowns are, equations are coming from the observation we just have. Okay, so we are less with the two conditions, equations actually, and those two equations we derive from the conditions which are called natural conditions. Okay, actually the corresponding spline is called the natural cubic spline. Okay, so natural cubic spline. Okay, what are those conditions? Those conditions says that the second derivative at the end point should be 0. What is an end point? x0 and xn. These are the end points. Okay, so second derivative at the end points is 0. Now if I ask you what is s second derivative at x0, s is nothing but a collection of sj's. Okay, so if you say x0, so x0 belongs to this interval. Okay, and corresponding to this you have s0. Okay, so let me just write s second derivative of x0 means s naught second derivative at x0. Okay, because if you want to take the approximation, or if you want to find the value of the s second derivative at x0, you have to choose the interval where s has a representation, which is s0. Okay, now if I just take the second derivative of s0, let me just write first what is s0. S0 is a0 plus b0 x minus x0 plus c0 x minus x0 square and b0 x minus x0 cube. Okay, so if you just take a second derivative and then you have to replace x with x0. Okay, if I just take the second derivative, this will be 0, this will be 0. Here you got c0. Okay, sorry, 2c0. Oh, here will be 2c0. Okay, then we have 6d0 x minus x0, and you have to evaluate it at x0. If you plug the x equals to x0 here, we got 2c0, and it says s second derivative at x0 is 0. Okay, so this is 0. Okay, so it means c0 is so c0 is 0. Okay, if you come here, you'll see with this you'll be able to find c0 as 0. Okay, now if you use this particular condition, now xn belongs to which interval? This interval. Corresponding value of s is this particular one. Okay, now if you just write that and use that particular value, you'll get cn is equals to 0. This is the conclusion. Please do that. Okay. So Cn will come equals to 0. As the C naught come from here as equals to 0, you'll get Cn is equals to 0. Okay. Now, these are the two equations that you got from the endpoints. So when they added to these, okay, you got total 4n equations. Okay, we got total 4n equations. So whenever we're using natural cubic spline, it means C naught and Cn will always be 0. Okay, they will be 0. Okay, so it's a natural cubic spline that we're using. You see at the top right corner, there is if you're using a natural spline, then these are the conditions. There are other cubic splines which are clamped cubic splines. Majorly we use natural and clamped cubic spline. But in clamped cubic spline, we need more information of the function. Okay, hopefully you remember from the last lecture maybe the clamp conditions are s first derivative at x naught is, and s first derivative at xn is this. It means I need to have more information about the derivative of the function. So it's a more requirement from the user, okay, which at times is not available. So that's why we normally use the natural cubic spline, okay? But we can also use the clamp cubic spline if these conditions are available, okay? Okay, ji. So now if you see this particular slide, this thing, this derivative, okay. So you see what is S naught? S naught is this, okay? Now if you just take the derivative, second derivative, here we got 0 because it's a constant term, okay? It's a linear term, this will also go to 0 because when you take a first derivative, answer will be b naught. Then you again take a derivative, it will be 0. Now if you take a derivative over here, it will be 2c naught, x minus x naught. Then you take a second derivative, it will be 2c naught. And if you take the first derivative, it will be 3d naught, x minus x naught square. And then you take a second derivative, it will be 6d naught, x minus x naught. Okay, now if you replace x with equals to x naught, this term will go to 0. We only remain with 2c naught. Okay, and this is equals to 0 by the natural conditions. Okay, that's why we got c naught equals to 0. Okay, okay. So I was saying that this is the slide which will give you all the AJs, BJs, CJs, and DJs. Now let's start a problem. Okay, and let's see how we can solve a problem using cubic splines. Okay, let me take an example. Okay. So we have a data. Zero one. 2.718 to 7.389 and okay, so we have a problem where we need to fit a cubic spline within the given data. Okay. Yeah. Okay, how many points we have? 4. So there are 4 points. Okay. Starting from x0, x0, x1, x2, x3. So this is x0, x1, x2, and x3. So the value of n is 3. Okay, the value of the x0, x1, x2, so on to xn. Okay, so if we start from the data point x0, the value of n in this particular problem is 3. Okay, so we have n equals to 3. So total points are 4. Now, if we just try to fit a cubic polynomial, a cubic spline, okay, here we will fit S0, here we will fit S1, and here we will fit S2. Okay? How many unknowns we have? 4 times the total equations. Okay, equations means splines that we're going to fit. Okay, 4 times, because in each spline we got 4 unknowns: AJ, BJ, CJ, and DJ. Okay, so these are 12. So we got 12 unknowns. Let me just write over here. What is S of x? S of x is S0 of x, S1 of x, and S2 of x. Now to have the value of A0, S0, I need to find A0, I need to find B0, I need to find C0, and I need to find D0. So these are the unknowns I need to find to have the value of S0. Similarly, to find S1, I need to have A1, B1, C1, and D1. Okay, and finally, just a follow-up. These are the unknowns I need to find. Okay, let's start with the first equation, which is AJ is same as f of xj. Okay, so A0 is same as f of x0. What is f of x0? It is 1. These are the f of x0 values. Okay, so A0 is 1. Because it is same as f of x0. A1 is f of x1. Okay, this is 2.718. And then we have A2 as f of x2, which is 7.389. We got an extra information. It will be used. A3 is what? We don't have to have it obviously at S3. We don't need that, but the value of A3 is there, okay, which is because AJ is same as f of xj. A0 is f of x0, so A3 is f of x3, okay. So I'm just writing over here because we will require this value. This is 20.085, okay. Now the step 1 is always find AJs, the step 2 is find now CJs, okay? Now since we are fitting a natural cubic spline, so C0 and Cn are 0. What is the value of n? It's 3. So it means C0 is 0 and C3 is 0 because n is equal to 3. C3 is 0, okay? So that is the precise reason why I have written n before, okay? C3 is 0 because we made a mistake that we make C2 as 0, okay? C2 is not 0, C3 is 0 because Cn will be 0. Okay, so we got C0 and C3 equals 0. These information is just coming from the natural conditions, okay? The conditions for the natural cubic spline. Now, the equation actually that we have in the step number 2, let's try to write that. Okay, so the equation is written over there. Let me just try it for j is equals to 1. Okay, for j is equals to 1. Or let me just write that equation over here. It is for cj's. Okay, let me write that equation. That equation is, please help me write that, hj minus 1, cj minus 1, then we have
hj minus 1,
hj minus 1
cj
plus
cj plus 1,
cj plus 1 is equals to 3 over hj minus 1, aj
plus 1 minus
aj plus 1 minus aj, and
minus 3 over hj minus 1,
and this is aj
minus 1.
Thank you so much. Now this is valid from j equals to 1 till n minus 1. Hopefully you get that why we take j from 1 to n minus 1, because this is the condition coming from while we're connecting the polynomials. So it is applicable on the interior points. So the interior points are not x0, they are not xn, they start from 1, they end at n minus 1. Okay. So we just take that equation from because this equation will give us the values of the unknown cj's.
It will be mentioned in the paper, or we have to try?
Okay, in terms of your exam, formulas will be available. Okay, you don't need to worry about that. Okay, you just need to make sure that how to use it in a particular problem. Okay, so that's why I mentioned the step number over here. While you're solving a problem, you have to go like this. Okay. Okay. Now, if j is equals to 1, let's try to do that. J is equals to 1. So if j is equals to 1, it is h0 c0 plus 2 times h0 plus h1 c1 plus h1 c2 is equals to 3 over h1 a2 minus a1 minus 3 over h0 a1 minus a0. Okay, you'll see like this. Okay, now what is the value of h0? h0 is x1 minus x0. Okay, this is h0. Okay, so that is h0 is the difference between the first 2 points. Okay, so which is 1 minus 0. h1 is 2 minus 1. h2 will be 3 minus 2. So they are same. h0, h1, h2 are all 1. Okay, so this is same as h1 and this is same as h2 in terms of a value, obviously not in terms of an expression. Okay, in this particular problem. Okay, they all are 1. Okay, so we got the values then. So here we can plug the value 1. Okay, c0 is already 0. Okay, here we got 4. Okay, here we have 1. Okay, and on the right hand side this is h1, which is 1. What is the value of a2? It is same as f of x2. We know these values. Okay, so we can plug just the information from there, and the unknown will be c1 and c2. You'll just see these two unknowns. Okay, now if I open for j is equals to 2, because I have to open till j equals to n minus 1, and the value of n is 3, so I have to open at j is equals to 2. Okay, so 3 minus 1 is 2. So one index will be up over here. Okay, so this is h1 c1, h2 c2, h2 c3, 3 over h2, a3 minus a2, and 3 over h1, a2 minus a1. Okay, similarly all things are available except c1 and c2. Okay, all the other things are the known numeric values. Okay, we know from our observation. Okay, before going to solve for c1 and c2, before going to solve for that, in this example, we got 4 data points. Maybe we have a problem where we got 6 data points. Maybe we have a problem where we got 10 data points. Practically speaking, we can have many data points. Okay? So you see, if for example, we have 101 data points, for example, so SJs will be total 100. We got total 100 SJs. So here, C0 will be 0. Okay? C100 will be 0. Okay? But we have to find C1, C2 up to C99. We have to find that. So it means here we'll have 99 equations. Okay, we'll have 99 equations. So we have to devise a strategy which is not particularly fit within this example, but it should be generic. Okay, so that's why I'm just going to write over here first equation that we got from which is C0 equals to 0 and C3 equals to 0. Because this is the information we got about C's from some other conditions. Okay, but we know them. Okay, so I'm just going to write all the information that I know about the CJs over here. Okay, now from here, if I just ask you, because you see, if we got 10 unknowns, if we got 5 unknowns, if we got 100 unknowns, you can't just manipulate the equation and find those values. This is the linear system you have. This is a linear system. Okay, you see CJs are what? The coefficient. What are the coefficients of CJs? They are some numeric numbers. Okay, so these are the linear equations you got. So you have to solve a linear system. Okay, so in which maybe you have to find C1, C2, so on to see whatever the value. Okay, how many unknowns? Let's try to write in a linear system form. Let's write the first equation. So what are the unknowns, particularly in this problem? C0, C1, C2, and C3. So these are the equations. We know some of them. Okay, we know some of the information. Okay, so let's write C0. If this is a linear equation, what is the coefficient of C0? 1. The coefficient of C0 in this equation is 1. What is the coefficient of C1? It's 0. It's 0. It's not here. It's 0. So it's 0. Then we got, what is the coefficient of C2? It's 0. And what is the coefficient of C3? In the first equation, it's 0. And what is the right hand side? It is 0. Okay. Now if I write the second equation, what is the coefficient of C0? H0. Then we have 2 times H0 plus H1 and, sorry, let me just try to write in a straight line, maybe. Try to write them. Okay, this is the second equation. And what is the right hand side? This is the right hand side. Okay, so this is 3 over H1, A2 minus A1, 3 over H0, A1 minus A0. Okay, this is the second equation. Similarly, the third equation, if I write, the coefficient of C0 is 0. Okay, so it is 0. Then we got H1, 2 times H0 plus H1, and this is H1. This is the third equation I have. Oh, thanks so much. This is H1, H2. Thank you so much. And the right hand side will take this particular form, which is 3 over H2, A3 minus A2 minus 3 over H1, A2 minus A1. And if I write the last equation, it will be this is the last equation, you see. Okay, as we got the first equation, the coefficient of C3 will be 1. Okay, other coefficients are 0. You see, this is a linear system we have to solve. And if you are having a lot of data, then obviously there are a lot of CJs then. Okay, so we have to solve this linear system. And what is the one good property of this linear system is there are many non-zero entries you'll see. Okay, but the only you see a lot of zero entries if it is a larger matrices. The only non-zero entries are occurring at main diagonal, okay, and adjacent diagonal entries. Adjacent entries to the main diagonal, okay. This is called a tri-diagonal matrix. Sorry? So what is a diagonal matrix? With non-zero entries only on the main diagonal. What is a tri-diagonal? The non-zero are only on the main diagonal and the adjacent diagonals, okay, to the main diagonal. Okay, that is a tri-diagonal matrix. Okay, now you will find the CJs from here. Generally speaking, particularly in this question, you can plug the value of C0 0 here, value of C3 here. So you can just solve these two equations. You'll be able to find C1 and C2. Okay, I have found it, and the value of C1 and C2 is, okay, let me just write over here. So the value of C1 is 0.756. I'm just writing up to 3 decimal places, and this is 5.83. Okay, these are the values you can solve from here. Okay, a very good property of this tri-diagonal system is this. If I ask you, is it a diagonally dominant matrix? Is it a diagonally dominant matrix? What is a diagonally dominant matrix? Their diagonal value is in absolute terms greater than the sum of the other entries. So it is a diagonal entry which is greater than the sum of. It is a diagonal entry, and here you see what is the sum? H0 plus H1. This is twice of H0 plus H1. Here you can say that H should be always positive, otherwise we can have a problem. Okay, so but if HJs are positive, then this is a diagonally dominant matrix, and if the matrix is diagonally dominant, you can always find a solution through Jordan and Gauss-Seidel methods. They are always convergent. Okay, so you can always find a solution of these systems. Okay, once we have the values of CJs by this, generally speaking this, and particularly you can just solve the equations. Now you can use the values of BJ and DJ given in these slides. Okay, you can just plug the values over here. If you see the expression of a BJ, it only involves AJs and CJs. Okay, and the DJs only wanted the values of the CJs. Okay, if you just plug it over there, the value of the BJs are, it is 1.466. I'm just writing up to 3 decimals over here, trying to write up to 3 or 4 decimals. 222. And the DJs are. So the equations are available to you. Okay? So now we are over with the step number 2. Now we'll go to step number 3. So we have AJs, we have CJs, we'll find the BJs. We just plug the values in this expression. And finally you'll be able to find the DJs. Okay? So the DJs come out as 0.25, 1.69, and 1.94. Okay? Sorry?
BJ or DJ के लिए भी फिर linear
नहीं, you don't have to make a system of BJs and DJs. It's just a direct, since you have, it's a direct substitution. Okay, so we don't have to do that. Okay, now you see we got our cubic polynomial. It's a lengthy process at times. Okay, but we got, because there are many unknowns. Okay, so but now we have the construction of S0, S1, S2. Okay, so if you just see this slide, okay, this is S of x we got. Okay, this is the S of x, where first we have S0, which is applicable from x0 to x1, which is 0 to 1. And then we have S1, which is applicable from 1 to 2, and we got S2, which is applicable from 2 to 3. Okay, Now, if you come to this particular problem, you can estimate the value of f of 1.5. By the way, if I just wanted the value of 1.5, which is the polynomial I'm going to use? S0, S1 or S2? S1, because 1.5 lies between 1 and 2. The corresponding is S1. Okay? So, if I ask you, just take the integration from 0 to 3 of f of x. How are you going to do that? If you have to integrate, so f of x, so the integration of f of x is what? It is the approximately equals to integration of s of x. And we know what s of x is. S of x is s0 from 0 to 1. It is from 1 to 2, it is s1. And from 2 to 3, it is okay? Okay? Okay, finally, if you just see this curve, these red dots are, what are these red dots? This is our data, the actual data. And that blue line is the cubic spline that we fit. Okay? That blue line is the cubic spline we just fit. You see, it comes very much in agreement with the behavior of the data. Okay? And okay, if I just ask you to integrate this thing, then what is the answer? 1 to 2 f of x is what? It is the integration of S1. Okay? And if you just see this curve, what we meant by integral from 0 to 3 f of x dx, it is the area under this curve from 0 to 3. And this means area under the curve under the portion from 1 to 2. So the second and the third red dot you see, okay, and the curve you see, my approximation will be like this. Okay, you see another curve here. It's a black curve going. So there are two things. A red dot and a blue line. There is one another line you see with a blue line. A little bit deviation, okay? So, obviously, ideally, we don't have the exact behavior of the data, okay? But we have generated this data from one actual function just to see ourselves that the spline that we're going to get, is it aligned with the data, number one, and does it align with the actual curve or not? That is the actual curve you see. Very minutely, you can see there is a difference over here, okay? That line is the actual line, okay? So, any questions?
Sir, black actually, sir, there is a black actually like red जो है वो.
Red are the data points, ना? So, whenever you have a problem, you only have a data. So you see like this, we only have a data, we fit a curve, then we say, okay, we got originally how the curve is going. So we just pop up that black line, the black curve, okay? So you can just, you can compare the performance of the cubic spline, particularly in this example, okay? Okay, in this particular lecture, we are able to perform the cubic spline interpolation, okay? And we can find the values of the unknown values, and we can also integrate, we can have an approximate value under the curve, okay? So in the coming up lecture, we will be doing one practical problems from your lecture number 1, okay? Along with the MATLAB implementation of the interpolation section, okay?